Okay, if you're taking a university calculus class or a real analysis class, then you really need to know these 4 rigorous definitions of a limit. And of course, later on I will have another video, 24 rigorous limit proofs for you guys. So you will learn how to write a proof for limit rigorously so you can impress your calculus friends and teachers. But here, we're just going to go over the definitions. Here's the first one. We have the limit as x approaching a of a function f of x that says this is equal to L. When we write this down, a and L are meant to be finite. And here's the thing. If we have L right here, we like to use epsilon. So let's go ahead and write that down. First, we have for all epsilon, which stands for error. For all epsilon greater than 0, and you see that right here it says x is approaching a, and here we like to use delta. So this is the classic epsilon delta definition. We start with for all epsilon greater than 0, and we say there exists a delta greater than 0. And what we are going to do is that right here, this is going to say the function can be as close to L as you want if x is close enough to a. So here's the thing. Once you tell me epsilon, this is how close you want for f of x to be close to L. And then you will be able to find a distance. Right there exists means that you can find a distance. And this distance tells you how close x is to a. Alright? So when this happens, f of x is going to be close to L. And this is how we are going to write down the rest of the stuff. For all epsilon greater than 0, there exists a delta greater than 0 such that, so what we said earlier is that if x is close to a, well, how close is to a? Delta away at most. And we're talking about close, we are talking about distance, so we use absolute value in math, right? So absolute value x minus a. If this is less than delta, again, it means that x is really close to a, just delta distance away, right? However, for this, a little note is that for the limits to exist, we don't care about when x is exactly equal to a. So sometimes you may have like a graph like this, but like an open circle, and then you still have a limit. We don't care about what happens when x is exactly a. So here we will say this is greater than 0. Right? So x is, we don't worry about if it's equal to a. Alright, so if x is close to a, then this implies, this is implication, that means we are going to get f of x is going to be close to L. So again, distance, so that's absolute value. We write f of x minus L. How close is close? The distance has to be less than epsilon. That's it. And of course, I have a detailed explanation on the epsilon delta definition where I use a specific value for epsilon and I work out the delta. So make sure you guys watch that and it will make a lot more sense. Now, for the second one, we have the limit as x approaching infinity of f of x that's equal to L. Again, L is finite, so we like to use epsilon first. So pretty much similar. For all epsilon greater than 0, there exists. But this time, what does x approaching infinity mean? It's not x minus infinity is less than a number anymore, right? Don't think about it like that. But rather, when x is approaching infinity, it means that x is going far, far, far to the right. So it's very different than this idea here. Again, x approaching a, it means that, let's say x is right, a is right here, and then maybe x is just approaching from the left, from the right, like this. But when we have x approaching infinity, it means that our x is going far, far, far to the right. Let's go ahead and use a different notation instead of delta. Usually, I like to use capital N. Some books may use capital K, but same thing. So we say there exists a capital N greater than 0, especially when x is approaching infinity. Sometimes you might have x approaching negative infinity, but this right here is a lot more common, especially This right here is a lot more common, especially when you are dealing with sequences. So x approaching infinity, we use there exists n greater than 0. Alright, such that we want x to be far, far, far away, big enough. How big is big? If x is bigger than the capital N, yeah, then we are going to get, so this implies, same thing like earlier, the distance between our function and L is small enough. So distance, which is absolute value f of x minus L, it has to be less than epsilon. Alright? Now, the third one, notice we have x approaching A, so it will be the same thing like the first one. We will be using delta, right? We have A and then just going from left and right, so we'll be using delta. But this time though, the limit is infinity. It's not a small error anymore. We want to make sure that the functions go up, 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 and up, right? So it's kind of like this idea, but this time it's the limit being infinity. So we are not going to use epsilon. Let's use another letter for it. Similar to this though, I'll use capital M. So we say for all capital M greater than 0, right? There exists, again, x approaching a finite number A. So we use delta, delta greater than 0, such that x approaching A, so same thing like this, same thing like this. When we have x is approaching A, right, the distance between x and A is less than delta, and we don't care about x is exactly equal to A, so we say that's greater than 0 once you read it backwards. This implies that, well, this time it doesn't make sense for us to say the distance between f of x and infinity. Instead, we just want to make sure that f is big, big, big enough. We want to make sure that our function f of x is greater than the capital M. Do we need the absolute value? No, we really want to make sure that f is positive itself, so absolute value there's no need. Alright, so make sure that you just pay close attention to all the inequalities and all that stuff. And by the way, there's pretty much no numbers except for 0, 1, 2, 3, 4, maybe 0 somewhere. Alright, last one. Maybe you can formulate this on your own, so I'll give you guys like 2 seconds to think about it. Pause the video, see how you can formulate it. Done? Alright, here's the deal. X approaching infinity, the function is also, approaching infinity. Because this is approaching infinity, we are going to say for all capital M, big enough, right? Any positive M, yeah? There exists delta, no, just kidding. X is approaching infinity, so we use capital N, right? That will tell you x is going to be big enough. Anyway, such that if x is greater than capital N, then we are going to get our function f of x is greater than capital M. Okay, so just like this. If f is keep going up and up and up, then that means when x keep going to the right, the function keep going up and up. So it's just like that. Of course, there are different small variations. For example, if we have x approaching A plus, so let me just make a little note. Especially this happens a lot when you have like an infinite limit. If you have this, then what we are going to use is that this is going to be, well, again, we are just going to have x minus A, but this time though, we just want to care about x approaching A from the right hand side, right? So if you think about what we did earlier, A is right here, and x minus A is less than delta, so we have this is A plus delta, and this is A minus delta, and x is anything between, yeah? But when we have this, we just have the right hand side. That means x minus A, right, is going to be less than delta. No absolute value, just one side. Also, make sure that this is greater than 0 without the absolute value. Similarly, if you have x approaching A minus, that means the left hand side, so you put a negative delta here, and then x minus a in the middle, and then 0 on the right hand side. So just like that. Alright, so hopefully all this kind of give you guys an idea, especially how you can see the difference and all that stuff. And let me just erase this because I like my definitions clean like this on the board. And you know it, as always, that's it. And make sure you watch the proof video.